for the invitation first, and good morning to all persons here. So I'll be talking about the stochastic Allen equation, which is a very well-known model, both in the deterministic and in the stochastic setting. And I will explain later what does it mean, Dobrushin boundary conditions. So we have this equation. So this is the equation we will be considering during all the talk. I have put this Maltese sign, so each time this Maltese appears, we will refer to this equation. And so to make things precise, we will be considering the solution M in an interval minus AB in R. So we are in the one-dimensional spatial variable. V is a two-well symmetric polynomial that attains its minimum value at two different points, M minus, that I will call for the moment M minus and M plus. Of course, M minus is minus M plus by symmetry. And I will ask that this potential, I will ask that it's zero at the minima, and it's also non-degenerate. So the second derivative at the bottom of the wells is non-zero. It's positive, of course, because it's a minimum. Epsilon is a small parameter that will go to zero eventually. And I'm considering space-time white noise. And the key point will be to consider the boundary conditions, which are A and B, going to infinity properly as epsilon goes to zero. So this will be the setup, and I will explain precisely, in fact, in which sense we consider the equation and how we impose which boundary conditions we are imposing. So let me draw a picture of the potential V so that we will keep it in. So it's something like this, simply. So here we have a minus, here we have zero. Minus down. Here it is zero, and here it is M plus. So this is V of M. Later on, I will take a precise example, but for the moment, any potential of these kinds will do. So let us, recall also that the equation can be written as a gradient type equation with respect to this functional. I'm not being very precise on the domain, etc. I will be later. So it can be written as a gradient type equation, which may help to understand what's going on. This is the variational derivative of f, and here we simply put in. So the derivative of this, I will call it an energy. This energy here is precisely the term upstairs. So this is the setup. As I told before, the equation has been very well studied, and I will recall some of the known results, very well known results, concerning this equation. So in the case we consider infinite volume, that is the spatial variable lives in the whole R, we have the constant profiles. You see, maybe I write the equation here. Remember, the equation was if we consider the equation in infinite volume, then the constant profiles, that is, if we take an initial datum that is constant in x and equal to this value m minus, then the deterministic equation will remain there forever. Same thing, of course, happens with m plus. And these are called the pure phases. This model is used in several contexts, for instance, and I'm using the letter M to recall models of spins. So the letter M would be, if you are used to these models, a magnetization. Otherwise, it's just the name of the function. So these constant profiles are identified with the pure phases of the system, and they are stationary for the deterministic equation, of course. They are stationary and asymptotically stable. Same thing, of course, this is completely symmetric, so we have two pure phases. So we need to have something in the middle. So those are called, I will call interfaces. So there is a stationary profile of the equation such that this stationary profile is increasing and connects the pure phases in infinite, from minus infinite, it's at the pure phase minus, and at plus infinite is at the plus phase. So it's known that there are these solutions, and the set of all the translates of these solutions, the set now is stationary stable for the deterministic equation. What does it mean? If we consider an initial condition of the equation, now we are forgetting about the noise. We consider this equation starting from a profile that is with initial conditions, which is this function m bar plus an error. Then as t goes to infinity, the solution will go to possibly some other set, some other profile, but still in this set. So the set M is stationary stable for the deterministic equation. It has a zero eigenvalue, the linearization around any of these things. So this is known, and let me write here, okay. M bar looks like this. For you to recall, each time I put a bar, it will mean an interface. So it's something like this. It goes to M plus so this is M bar of X. And we will think at these things as interfaces. So M bar of X will be the centered one. It's centered at M, this is 0. And we will call M bar Z of X this function translated by Z. And we will think that M bar Z of X represents an interface located at Z, although it's not a proper interface in the sense, in the sharp limit, you will see as a step function, but we are keeping, it can be seen that it goes exponentially to its limiting values at plus minus infinity, but still it's a diffuse, some kind of a diffuse interface. But we will think as an interface, and the localization will be Z. Now, when you add a noise, a small noise to the equation, this result is known, that the solution, I don't know if I'm able to, okay, here, okay, you take times that grow as epsilon to the -1 and as epsilon goes to 0, and consider the solution. So what the first part is telling you is that the solution is close to a shifted interface. It's randomly shifted by this x epsilon of t, which is it's a random shifting, it's a process. And this process, when scaled correctly, goes to a Brownian motion. The scaling is what you would expect of the scaling, because we have a square root of epsilon in front of the noise. I should now turn the noise on. So, where's the eraser?
No.
Under your laptop?
Oh, there are many of them. Thank you. So this is what we have. And this is a well-known result. It has improved by Presutti, Demasi, and me some time ago, and also by Funaki in the sharp interface limit. So what happens when we impose Neumann boundary conditions? Okay, still we have the constant profiles. They satisfy the Neumann boundary conditions, so they are still solutions of the equation, the constant profiles, and they are still absolute minimizers of the energy. But now we don't have this whole, because imposing these conditions, the shift invariance does not hold anymore. So we have a pair of stationary solutions, which I will be calling plus minus m star, and they go to an interface located in the middle point as A and B go to infinity. But they are now saddle points. I mean, for each fixed size, of the interval, there's a finite number of stationary solutions of the deterministic equation, and the first two are stationary, stable, and the other, they are saddle points. The second, more stable stationary solutions are those ones, and they have, as it's written there. So if we take an initial datum close to m bar, but of course we have to do something with the boundary conditions, the solution of the deterministic equation moves along this set m towards the endpoint with a velocity which is exponentially small in the distance to a. This is for the deterministic equation. So what happens? We have now boundary conditions. So we start at time 0 with something like this. We have here minus a and Neumann boundary conditions. So the pure phases are attracting everybody. So this should go to either m plus or m minus. So how will it go? It will move, keeping its shape. It will move like this, for instance, as time. So in this direction, for instance, or maybe the other, and the velocity of the traveling front is exponentially small in the distance to the endpoint. So if we take a of the order of the log of epsilon to the -1, so since we have an exponential, at time scaled by epsilon to the -1, the drift takes over, and for instance, the minus phase extinguishes. So suppose this is A, and we started with something which was slightly to the plus. So this will move like this until it reaches some point here. I mean, it moves exponentially slow until the scaling is such that it will deterministically, of course, because it's a deterministic solution, but it will go fast towards extinction. This is how the dynamics goes. So, and these are results of Karen, Tego, and Fusco, and Hale, and many other people. This study of the slow motion of the interface for the deterministic equation. So, what happens in the presence of noise? So we put noise, and then what happens? This is also known. If we take A, okay, so let us think that we are taking B of the order epsilon to the minus beta. This is, I want to forget about B. B is very far away. Okay, and A, I will take of the order of the log. So this A is much shorter than B as epsilon goes to 0. So what happens is that in the presence of noise, if we take A like C log of the epsilon of the minus 1 and B very, very large, infinite if you want, then the fluctuations dominate and the interface oscillates with a Brownian in time scale epsilon to the minus 1. That is the same result as before. In this scaling, the boundary conditions are not seen. See, for C log epsilon to the minus 1, with C very large. But if C is smaller than the right C to see things in epsilon to the minus 1, you see, we want to look time scaling of the order of epsilon to the minus 1 because my noise is fixed in this scale, in this scaling here. So I repeat, I fix this scaling for the noise and I take this scaling for the endpoints. And it is for normal boundary conditions, this is known. If C is large, you don't see the boundary conditions, the interface doesn't see the boundary conditions and oscillates like a Brownian. But for C smaller than C0, which is some critical value there, then the drift will dominate the fluctuations and the noise won't be seen and the interface will go towards extinction with a velocity, with a fixed velocity. But this can be seen looking carefully at old works. But what I want to do now is to impose different boundary conditions. So I want to consider same equation, but with boundary conditions that fix the endpoint, fix the different phases at the endpoint. That is, I put fixed value m minus and fixed value m plus and minus and plus infinity. See, so and this I'm calling Dobrushin boundary conditions. So I'm taking m of minus 1. Excuse me, minus a. So I consider this equation with these boundary conditions.
What's wrong with calling them Dirichlet?
With Dirichlet?
Yeah.
Okay, I hope it becomes clear afterwards. We can study Dirichlet, but it's not very interesting because what you want to do?
They are non-homogeneous Dirichlet boundary conditions.
Sorry?
They are usually called non-homogeneous Dirichlet.
Yes, also. But in the context...
That's my question. This is Dirichlet condition.
Non-homogeneous Dirichlet boundary condition. Oh, I was thinking that you were asking about 0.
No. I was asking about this.
Okay, Dobrushin boundary conditions, because in the context of Gibbs measures, it's interesting. I mean, it's a thing that they do. They put one phase I mean, of course, normally in dimension 2 or higher. They put one boundary condition on, and they put minus boundary condition, and so they study how it evolves and to get uniqueness on of the Gibbs measure in certain. So comes from another field. It's okay. It's non-homogeneous boundary conditions if you want. Okay. In this case, since we have broken the symmetry also somehow and the shift invariance, there is a unique stationary stable profile. We have no longer, the pure phases are no longer solutions of the equation because they don't satisfy the boundary condition. So in this case, there is a unique stable profile that I will call M star. And as you could imagine, this M star, I will write it here, M star looks for A and B large something like this. This is misleading. This is not the center. It's the center of the interval AB. So this is minus B and okay. Something like this. But here we have the proper. So something like this is the unique. This is M star. The unique attracting profile. And now, what we want to do is to choose a scaling for A, the left end point, such that we feel both the effect of the noise and of the boundary conditions in the limiting motion of the interface. Okay, we want to choose A in this way. So, to do that, I will fix a particular instance of V, which is this one. This is a particular instance. V is 1 over 4, it's a normalization. This a potential like that, satisfying all the hypotheses, but only in this case we can compute everything. So in particular, the pure phases are plus and minus 1, and the interface is the hyperbolic tangent of xt. Can be computed, and things are normalized so that you get this. Okay? So now, and from now on, I fix this potential V, and so we get these values for the pure phases and the interfaces, and now I choose A is 1 over 4 the logarithm of epsilon to the minus 1, B is epsilon to the minus beta, and the reason it could be any beta, so think if you want that B is infinite at this point, so you don't see the other boundary condition, the other boundary you don't see. And I'm choosing another scaling that I will show how it appears, lambda, the logarithm of epsilon to the minus 1. So A is going to infinite, B is going to infinite much faster, and we have this scaling. And now I consider M the solution of the equation with Dobrushin boundary conditions, imposing minus 1 and plus 1, and an initial condition that is, the initial condition is very, very close to an interface in infinitable, in subnorm. So let me say that I will.
You take initial condition depending on epsilon.
Yes, yes. The distance to the interface, it depends on epsilon. We cannot take exactly M bar because it doesn't satisfy the boundary condition, so you have to do some proper, okay. And okay. So in what follows, I will be talking about continuous functions, and in what was before also. So we consider, in which sense we consider these equations. We consider these equations. We write a corresponding integral equation and solve this integral equation. And so this is called sometimes a mild solution, and it can be seen that the mild solution is a continuous function of both variables x and t, and it exists forever, and so nothing strange happens. So I will be talking always about continuous functions. So so finally the setup, and now I can state the first result, which is this. So there exists a real adapted, and I should say also continuous process, x epsilon, which is the random shifting of the interface. So if we start, this is a mistake because I'm putting this epsilon. Okay. This epsilon there, I mean, I'm not using it. It's to recall that it depends on epsilon, but I'm using m only. So there exists a process such that the solution at every time that goes as long as epsilon to the minus 1 times lambda, remember lambda was a further scaling. For any t in this interval, the subnorm of the solution is close to a randomly shifted interface. So the solution follows this interface, this moving interface, with probability going to 1 this way. So in this time scaling, the solution is a shifted interface. This is nothing new. This is, I mean, it is new in the sense, of course, there are some technicalities involved, but nothing very different from the previous results. But here there is a difference. Now we consider the random centering of the solution. So this is a continuous one-dimensional process. We scale it by epsilon to the minus 1, which is the right scaling, and we see that the solution converges to the solution of this one-dimensional stochastic differential equation. With a Brownian motion with some diffusion coefficient. So the interface moves, now filling this drift, plus the Brownian motion that we had before in the case of for instance, Neumann on an infinite volume. Then you feel the interface feels this strong drift. So we call this a soft wall effect coming from the boundary conditions. Because what happens? We have here A. I will ignore B. So we start here next to 0. And so since the volume is going to infinite, the dynamics remembers the infinite volume dynamics. So this will be the Brownian. But since the pure phase is fixed here, minus 1 is fixed here, then it somehow repels the motion putting it back at 0. So it doesn't want to go to A because it would violate the boundary conditions. So it's kind of a soft wall because it's a strong drift, but it's still a drift everywhere. It could reach any negative value. It doesn't want to go in the negative, but it could go with small probability, but it could go. And now,
what am I missing here? That diffusion seems to have a positive drift.
Yes.
What's asymmetric about the problem? I missed something.
No, when positive, yes, because it positive, it means it pushes when y is negative, it pushes the interface back. So it's positive in this sense.
But when y is positive, it's still pushing it to the right.
Yeah, but when y is positive, I mean, it's almost 0. It's constant almost.
It's still asymmetric, and I don't.
No, it's not symmetric.
Okay, go ahead. I mean,
Why? Why is it not symmetric?
Because it's an exponential.
Yes, but
no.
why
But
do
the
you
problem
get this?
seems
Exactly.
Ah,
I
okay.
understand.
Okay. Because I'm putting B very large, so I'm not feeling anything from B. The interface is
A is fixed and B is large.
no. A is not
Oh,
fixed. A is going on the A is going like 1/4 exactly 1/4 logarithm of epsilon to the minus 1 gamma, and B is epsilon to the minus B. This probably goes epsilon to the minus beta. Okay. So now we can do this further scaling, which is okay. Recall lambda was logarithm of epsilon to the minus gamma. So under this larger scaling, the process. Remember, x is the random shifting of the interface. The random shifting of the interface goes weakly to a Brownian motion with the same diffusion coefficient reflected at 0. So in this further scaling, the repulsion from the boundary becomes sharp, and it wouldn't go to the negative. So the drift, if it's simply, if you scale this, this is not, of course, allowed because it's the same epsilon, it's the same. But if you scale the limiting process by this scaling, you will get an infinite drift, a drift going to infinite in the negative part of the axis, and 1 on the positive part of the axis. Just it's an easy computation. You write down the corresponding integral equation and scale it, and you get something that will converge. You get something like an infinite drift on the negative and a 0 drift on the positive. This is reflected Brownian motion. Okay. So this is the main result concerning the non-symmetric case. Oh. Well, I don't know. If I have time, I will come back to give. I will try to give an idea of the proof. But now let us consider the Allen-Cahn equation in the symmetric interval with this precise scale. So now we are in the symmetric case, and I will keep L, but in fact we only have epsilon because L depends on epsilon explicitly and definitely in this way. But I will keep L. You will see why. So. So we have this result. Still, in the same scaling, there is a real adapted process such that the solution follows the interface randomly shifted. And what's the limiting behavior of this interface? It's given by this equation. So now we have a symmetric equation. You see, if you remember before we had minus 12, I think, e to the minus 4 something, and now you have from B, also this effect. So you compose a hyperbolic sign. So you have repulsion from one endpoint and repulsion from the other endpoint in this precise scaling. Okay, so you may ask, what happens? I want to comment this. The result and also the previous one are sharp in the following sense. If we take A so if we take A equal 1/4 plus delta logarithm of the, let us say, well, in both cases, L. the symmetric case, we take L, something slightly larger, that is delta is positive, then the logarithm of epsilon to the minus 1, then the results would be totally different. The drift does not appear, and we obtain a Brownian motion, just a Brownian motion. That is, in this case, we have a situation like infinite volume. That is, no drift. The boundary effects are not present. So this is taking, now taking L equals for minus delta. This is finite volume. That is, the interface evolves deterministically to the unique minimizer. So it goes to the center of the interval, deterministically, because there is, in fact, there is infinite volume. What do you have? We have a potential with a unique minimizer. So the solutions should go deterministically to the bottom of the potential. So this is what happens in this scaling. Okay, so there is a precise point where we obtain this kind of result, and this 1/4. This of course depends on the potential we have chosen. So.
What if you change the square root of epsilon in front of your noise? Would you get the same type of conclusion?
Yes, I mean, we just have to rescale, because it's a unique scaling I'm having, if you think.
Yeah.
If you rescale everything with the noise, it's the same. But, okay, perhaps, I mean, someone prefers to think it in another way but once you fix this, then it fixes all the subsequent scalings. The time scaling and the volume scaling and everything. What you could do, I imagine, is to take a further scaling, probably in front of here, to get the sharp interface. But this is another thing. Okay, so recall that the invariant measure for this process is this one. It's a very easy computation. So you compute the invariant measure of the process. Okay? Now, remember that we have defined the energy functional. We have written, remember, the equation as a gradient type equation with respect, very differentiating with respect to this potential, which is properly defined in this space. And again, if L, now we are in the symmetric case. In what follows, I will be in the symmetric case. Now, if L were infinite, then the potential would have an infinite family of minimizers. This set M with all the hyperbolic tangents shifted. So those are this in infinite volume. This energy is shift invariant, and those are the minimizers of the energy. You can even compute the value. This is called the surface tension. I don't know. For each L, on the opposite, for each fixed L, the energy has a unique minimizer. We have seen that before. This minimizer converging, now we are in the symmetric case, to the centered hyperbolic tangent as L goes to infinity. So, for each z, let us define the difference between the value of the energy at an interface at the value of the energy at the unique minimizer. And it's not difficult to see that we have a behavior which is of the a limiting behavior of the order of the exponential of minus 4L. So we define this functional GL, normalize it in this way to obtain, otherwise we would get 0, normalize it in this way to obtain a finite limit. And we call this functional the excess free energy. It's related to the energy necessary to shift the interface in finite volume. So you have to pay something to shift the interface. But you have to pay very little. You have to pay of the order of e to the minus 4L. And the next result is the following. This functional converges, as L goes to infinity, to this function. So it's infinite outside M, but it goes to a finite function inside the set M. That is, somehow the functional FL remembers that it used to be an infinite volume defined energy, and so it keeps a finite volume on this set M. On the set, remember, M was the set of all the shifted interfaces. So we prove this, and now consider the probability measure formally defined. This is something that makes no sense. It's just written there to give an idea of what it is. I will think that you have this function, this measure defined on the set where the functional was defined. Z is a normalization, and this product there, it's Lebesgue measure in infinite volume or something like that, doesn't exist. So, but rigorously this measure may be defined as the invariant measure of the process, giving us the solution of the stochastic, the process we've been studying. So we have this process. Now, x belongs to minus L. L, remember, is going to infinity with epsilon also. But for each fixed L, that is for each fixed epsilon, there is an invariant measure. And the invariant measure would have this form, this formal or informal form up there. So what happens? If now suppose L remains fixed and the noise goes to 0. Well, we are in a finite volume situation, and it is well known that the measure, the invariant measure, will go to a delta on the unique minimizer of the energy. We have a potential, I mean this energy, with a unique minimizer, so the invariant measure will go, if I repeat, if L is fixed and epsilon and the noise goes to 0, then the measure goes to a Dirac measure on the configuration. Well, it's not there anymore. The configuration, remember, this which is something like this. On the other hand, this measure satisfies a large deviation principle with this exponent. Again, for L fixed, and large if you want. But from the previous theorem, we proved that FL of M bar minus FL of M star times e to the 4L converges to something. So this suggests that a joint, if we take a joint limit, L going to infinity and epsilon going to 0. So in this way, then this large deviation principle that holds for the invariant measure suggests that we may obtain a non-trivial limit. So in fact, this is true. If we consider this space, which is the space of continuous functions that go to plus minus 1 as x goes to plus minus infinity, then the invariant, let me explain this carefully. In this space, considered with the subnorm, the measure mu epsilon L, in fact, depends only on epsilon because we have fixed again L. Okay, it's not there. Remember L. We are in this situation. So this invariant measure converges to a measure mu. And what's this measure mu? This measure mu is a measure which is concentrated on M, that is, it's concentrated on this space of shifted profiles, and on this space, it's described as it's there. So what's the measure of a set? It's this mu hat over the interfaces such that mz is in A, where this mu hat is precisely the invariant measure, remember, for the one-dimensional process describing the interface. So what we have obtained is an invariant measure in a joint limit, volume going to infinity and noise going to 0, which is non-trivial, non-translation invariant, and so and is precisely described in this way. So in order to obtain this result, we had to obtain to write the measure mu of epsilon L with the help, I mean, to describe it, there are many ways of describing this measure. One of them is the invariant measure of this process. Another would be, I mean, it has a density with respect to a Brownian bridge going from -1 to +1, but this is not very useful. I mean, we couldn't manage with this representation, so we had to take a representation depending on a non-homogeneous drift, and so using this representation, we could prove that the measure is tight in this space and that it's concentrated on a small tube around M. Once you are there, from the dynamic behavior of the interfaces that I told you in the previous result, then you can see that the limiting points, you can characterize the limiting points. For the dynamics results, I wanted to show you how you, sorry, I don't know how to go. Okay. Let me show very quickly an idea of the proof, or at least, I mean, how it, and it's related also with the question of this Dirichlet boundary condition. So we here we have a linearization of the equation around m bar z, which is not, it is a solution of the equation not satisfying the boundary conditions. But we can do this linearization. But so downstairs, what we do is here, what we do is we write down the corresponding integral equation in terms of this operator, GTZ, which is the operator corresponding to the linearization around the interface. But we have to correct, I mean, with Dirichlet boundary conditions. Now Dirichlet 0, 0. But then we have to put a correction to obtain the proper boundary conditions. So we get this equation, which is equivalent to the original equation, but written in terms of these operators because this will be useful. It's complicated. There are simple ways of do that, but this is the useful thing. So, okay. It's not difficult to prove from the equation, from the integral equation, that for times that are not epsilon to the minus 1, but much shorter, still going to infinity with epsilon, it's not difficult to prove that since we started, remember, very close to the center of the interface, we are still close to the center of interface in this times, in this scaling time. But now we have to define the center because we want to follow a random profile, and so we want to define a centering. We want to associate to each profile a point, and this point will be the process X that it's moving. So there are many ways of doing that, but the proof that proved useful is this one. For a configuration F, we define the center, okay, by this formula, but this it's a good. No, it's not the formula. This is a good approximation. The formula is, okay, take the center as the center of the interface that minimizes the L2 distance of the profile. So you are given a function f, which is close to m somehow. Consider the difference of f to the points of m, and choose the center of the profile in M that minimizes the L2 distance. So this is a good approximation, and so what you can do is, okay, take the evolution. This will be the center at time t, at that time k plus 1 times t, and this will be the center at time kt. So this is a good approximation. What you do is just get the integral equation that was in the previous slide, project over, this is the first eigenvalue of the linearization, so project, and we get this. So this is an integral equation for the increment, for the infinitesimal integral, for the infinitesimal difference of the centers, of the evolution of the profile. So, because the profile is close to an interface, so you want to say, how is its center moving? So this is an approximate equation for the centers. And from here, you can see the result. Okay, here we have something, we have a spectral gap for this operator, so this is the first eigenvector, so this won't contribute. Here, we have okay, I will see this term. Here we have the nonlinear terms, but since we have linearized around m bar, the nonlinear terms are smaller, of smaller order, so they won't contribute. It's not easy to get rid of them, but you can see that this won't contribute. In fact, you have to sum them up and to see in the limit. I mean, it's involved, but you can see that they don't contribute. And here, we have a Gaussian, no, it's not a Gaussian process. Conditioned on the center, it is a Gaussian process. And conditioned on the centers, you can estimate its variance, and they are independent conditionally. And so, from this term here, you get precisely the Brownian motion. And the drift comes here, as it should be, because the boundary conditions are precisely on this function phi. And so phi has to be very carefully estimated, because you see, a logarithmic error is already a disaster. So you have to do very small errors. And so this term, we can see that it is of the order of this term, where lambda 0 is the first eigenvalue of the linearized operator, and psi is the first eigenvector. They are close to the corresponding eigenvector and eigenvalue of the operator in the whole volume, but okay, the difference can be estimated, and so here you have the drift. Here you have precisely, okay, apart from some constants coming from here, the exponential to minus 4z and the exponential of minus 4a will give the power of epsilon necessary to add up at the end. So here you can see the drift. And this is similar to what happens with the Neumann boundary conditions that I told you that at the end you have a drift leading the interface to extinction, leading to the minus phase to extinction. Here you have the opposite sign, so you have this repulsion from the boundary in this precise scale. So I have at the end some, excuse me, some references, and thanks for your attention.
Thank you very much. So, questions and comments? Yes?
If you go back to the previous page where you showed the idea proof, my question is related to the choice of the random perturbation. I'm not really sure in what way the choice of the random perturbation influences your analysis. What characteristics of the square root of epsilon b wxt are used in the analysis? It looks to me as long as you have that term going to zero there.
No,
Yeah.
here.
So it's just the last term, basically, that comes from.
No, the important, excuse me, the important thing is here. When you project this noise here, we obtain
That term is going to zero, am I right? That's the
no, it's not going to zero. No, when you, and of course it's going to zero because this is infinitesimal.
yes.
But when you sum up, it goes to a Brownian motion.
All right. Okay. So
It-
what you
no.
need is something that gives you in the limit a Brownian motion.
Yes, it yields a Brownian motion, and no, and the precise constants comes from this normalization. This 3/4 that we carry, I mean, I don't know if you remember, the 3/4 in front of the Brownian motion comes from here. So this is, this is conditionally Gaussian. This is kind of a central limit theorem. Conditionally, it's.
Anything else in here, as long as you have a limit, then that limit would appear in the equation for x. That's what I'm trying to say. I mean, the fact that you have a
Yeah, probably you get different constants and so on. You mean if you put some
anything else? So you think of
no,
it
and I don't think anything else, because you use independence. It's very important. You are using a central limit theorem.
Sure. In this particular case, because you have the independence, what I'm trying to say is that as long as you have a limit of that term to something which is meaningful.
No, because you have to sum up the terms, and you have to recover a Brownian motion. This is kind of a discrete version of
X.
the equation, of the stochastic differential equation that we obtain in the limit. So if you want to obtain a Brownian, then what I'm saying is you can put things in front here. This doesn't matter. I mean, but I think you still need the noise to be white noise. You can put functions in front of the noise if you want to kill the noise outside or whatever, but I think it's important that the independence properties of the increments of the noise.
No? Stella?
I'm wondering about when you have how to compare the stochastic equation with the deterministic when epsilon is 0. Did you say the measures, the support of the measures in the stochastic case converge to that m bar?
Mhm.
Is it true?
Yes.
Support of the measures for the stochastic, the invariant measure of the stochastic equation.
Yes.
Did they converge to the
To the m.
deterministic support?
They converge to m. To
M bar.
the support converge to m, not to m bar, to the whole m, to the whole all the translates.
And you know how quickly that goes?
No, I don't know. But I don't think I
It's
know.
like a Lyapunov exponent. How does it compare with the deterministic case?
Mhm. No, but in the deterministic case, I mean, what do you mean the deterministic case?
Well, when there is no noise.
Yes, but so the volume is what? Mm,
Well, you see, you have a unique stationary solution with epsilon. Is that okay? That's correct? You have a unique stationary solution.
yes,
So there is a rate of convergence to that.
yes. This,
That's exponential.
yeah, but it's not converging to something that it's related to the. It's not converging to a delta. I'm not sure I understand your
Anyway.
question. Okay.
I think it's certainly, you have time to discuss this question later. Not necessarily today. Some more questions, comments? If not, let us thank Sandra again.